Hello students, welcome to my YouTube channel Concept Clear. Here I am making different videos to clear your concept which may not be clear in the classroom. So I'm hoping that I will get some benefit by watching this video. So let's go to the topics we are going to discuss today. Today I'm going to discuss about minimum delay constraint of flip-flop based sequential circuits. So what is the expression for that? What is the expression of minimum constraint delay or minimum contamination delay of the combinational logic circuits, which will be used in the flip-flop based sequential circuits? Let's go to the topics. In the earlier video, already I have discussed about what is a flip-flop based sequential circuits, how to find out maximum delay constraint of a flip-flop based sequential circuits. If you want to see that, you want to understand that video, you can watch in my channel. So now I'm going to discuss about minimum delay constraint of flip-flop based sequential circuits. So here you can see that this is a flip-flop 1, this is flip-flop 2, in between one combinational logic is given. So based on that flip-flop based sequential circuit, over a one clock cycles, one flip-flop will be there. So this is flip-flop 1, and in flip-flop 2, this distance will be a clock cycle, that is TC we are considering. Okay. So now we know that flip-flop are edge triggered flip-flop which will be active when a positive edge of the clock will come, and with respect to that, the data which is given input to the flip-flop, it should satisfy the setup time and hold time. So now what is setup time and hold time concept? For understanding that, I already makes one video for setup time, hold time. You can see that. Now coming to here, let us draw the waveform. Already I have done. This is the clock signals phi. Then I have this is the output Q1. Next, this is the output of combinational logic, that is D2. Okay, D2, this is Q1. First, see here, for a flip-flop based sequential circuits, the data is given input to the flip-flop 1, then that output Q1 will be passed through a combinational logic, then the output of the combinational logic D2 will be given to the next flip-flop in the next coming positive edge. Okay, so now I'll show here the waveform. Now this is your clock signals. So this is one active edge or positive edge. So here the active edge means the flip-flop will be active at this time. Again another active edge is coming here, positive edge. Here also the flip-flop will be active. Remember that these clock signals phi is connected to both. Here also it is connected phi. Here also is connected phi. Means same clock signal is connected to flip-flop 1, flip-flop 2. That means when flip-flop 1 is active, at the same time flip-flop 2 is active. Then what is their job? Flip-flop 1 job is to transfer the D1 data to output Q1. Flip-flop 2 job is when the active edge will come, it has to transfer the data D2 to output Q2. Okay. So now we'll understand this one, how the minimum delay constraint expression is calculated. So in this rising edge, in the first clock rising edge, let us consider here flip-flop 1 is active. So when the flip-flop 1 will be active, then the D1 will come to Q1. It will take some delay. So if you are taking this active edge, then you are getting data here. So this delay from the clock edge, active edge, to this output when it is starting changing, that is known as contamination clock to Q delay, TCCQ. Already I have discussed this thing. Again, this Q1 is given input to the combinational logic. So combinational logic will have some delay, then you will get the output D2. The delay after which the output starts changing, that is known as contamination delay. So if you are giving Q1 after a TCD contamination delay, you are getting the output D2 start changing at this point. Then after a propagation delay, the output will be stable. Okay, so that means from this point to this point is your CCQ, contamination delay from clock to Q. This is contamination delay from the data is given in the combinational logic. Okay, so when the data you are getting here D2, then after some time the D2 data will be stable data after propagation delay. So now it is constant here, you can see. Then we'll go to the next positive edge. When the next positive edge is coming, this positive edge is given to flip-flop 1 as well as flip-flop 2. What flip-flop 1 will do? It will take the new D1 it will take, and it will give a output Q1. Let us consider the second output that we are getting, that is Q1 dash. Next, that Q1 dash will be given to the combinational logic, then it will give an output, a new D2, that is D2 dash. So previously this is the output. Now in the second rising edge, when it is coming, the new D2 dash will come. So D2 and D2 dash both are same. So you can see that in this case how Q1 dash is coming. This is the rising edge. At the rising edge, after some time Q1 dash is changing, then after some time it is become stable. Then this clock to this Q1 dash, when it is starting, it is known as TCCQ, contamination delay from clock to Q. Then this Q1 dash is given input to the combinational logic. It will take some delay, that is known as contamination delay of combinational logic circuits. Then the output D2 dash will start changing. So this is known as TCD. Okay, so now what things you should understand here, whenever this rising edge is coming, the D2, old D2 will transfer to Q2, and new D1 will create a new output Q1 dash, that will also create a new output D2 dash. Now this D2 is your old D2, this D2 dash is your new D2. Now old D2 will exist till new D2 is formed. Once new D2 will come, then old D2 will not be there. So new D2 will taken over than old D2. So now you see here, so up to this, if you are seeing, for example, up to this time old D2 is there, old D2 is equal to new D2. Once the new D2 is coming, then this old D2 data will be not exist, the new D2 will come here. Okay, when the new D2 is coming, old D2 data will not be present here, it will be taken by the new D2. That means at this time it is taking, the new D2 is changing. Understood? Then what is the drawback if it is happening there? See here, we already know that flip-flop 2 or any flip-flop, if it is satisfying the setup time and hold time, then only the flip-flop will give a correct output. Now for example, in this rising edge flip-flop 2, at this point, this is your setup time, so it is satisfying the setup time. But if the whole time, let us consider this one, this much is your whole time. That means up to this, the input data D2 must be constant. But because of the CD, contamination delay of combinational logic, now D2 is changing here, means D2 is changing here. At this point D2 is changing, it is not constant. So then at the flip-flop 2, whole time violation will occur and you will not get a proper output at this flip-flop 2 output terminal. That means Q2 will have some error. Then how this error can be rectified? The error can be rectified in two ways. First, the hold time can be decreased, or the contamination delay can be increased. If the contamination delay, now here I will make at this point, so this is equal to this one. If the contamination delay will become here, then what will happen? Contamination delay and hold time at the same point, so it is satisfying the hold time criteria of flip-flop 2, so will not get any error at the output. That means what is the delay here we are seeing? This is TCCQ, and then because of contamination delay we are taking this one TCD. This should be greater than equal to T hold. Then only there will be no contamination delay. Sorry, there will be no error output will get. Then what is TCD expression? TCDB should be greater than T hold minus TCCQ. This is the expression for minimum delay. Okay. So once again I will tell this thing in briefly. First, in the first clock cycles, when the positive edge is coming, this flip-flop 1 will pass the D1 to Q1. Then the Q1 through the combinational logic we are getting D2. As I am showing here, this is coming here. After a contamination delay TCCQ, we are getting Q1. Then after another contamination delay TCD, we are getting D2. So now D2 is starting changing here, and it will be stable after some time. So here the stable. Now when the second positive edge is coming, this D2, which is the old D2, is behave like an input to the flip-flop 2. At the same rising edge, flip-flop 1 also will take new D1, and it will create a new Q1, that is indicated as Q1 dash. That Q1 dash will pass through a combinational logic. It will also create a new D2, that is D2 dash. Now D2 and D2 dash are not different. They are same. D2 is your old and D2 dash is your new. Till new D2 is not coming, old D2 will be there. Once the new D2 will come, then old D2 will be not there. Old D2 will be taken by new D2. So now if because of contamination delay, if you are getting the changing of the D2 at this point, then what will happen? If the flip-flop 2 hold time is this much, then it is violating the hold time, because hold time means the data must be constant, but now here the data is changing. Then we will not get a proper output. So what we can do this one, either we can decrease the hold time up to here, or this contamination delay can be increased up to this point. Then if you will see from this clock, if you are taking this is TCCQ plus TCD, this is the contamination delay. Then from here we are setting the hold time. So this delay TCCQ plus TCD should be greater than equal to T hold. Then we will not get any hold time violation. Then TCD should be greater than T hold minus TCCQ. This expression TCD or contamination delay is known as minimum delay of the combinational logic circuits, for which we will not get any error at the output of the flip-flop 2. Okay, this is known as minimum delay constraint of flip-flop based sequential circuits. Hope you understand this explanation. If any doubt will be there, please ask me in the comment section. I'll try to rectify, or I'll try to solve your doubt. Okay, thank you.